Buenos días. The first lectures, the two previous ones, this one, the next one, are the different sides of one and the same picture. So these lectures are independent on each other, but on the other hand, they discuss the similar questions. So lecture today will be case of persistence related to Henon maps. First of all, I will give the title just Lecture 3, Case of persistence. So we are still dealing with the Petrovsky-Landis strategy. There is some space of maps, finite dimensional, not the previous one, not polynomial vector fields in the plane, but rather polynomial automorphisms of the plane. I will describe them in more details in a few minutes. And we have the space of maps. We discuss some property of these maps, and we want to prove that a general maps, generic maps, has that this property is bad. We prove that there is no open set of maps with a bad property. So there is a bad property no matter what one, and we want to prove that there are no maps, there is no ball in the space of maps with this bad property. We suppose the contrary. We suppose that there is a ball with the bad property. Then we are sure that there is another ball where the bad property is not met at all. Then we suppose, then we want to prove that if we continue along some path from the bad to the good domain, if there is identically a bad property here, then it may be carried on along this path to this domain, that is, persistence takes place. And then we will get a contradiction. If we have a persistence, then we will get a contradiction. I explained you the idea of Petrovsky, how this picture might work for the limit cycles, but was not confirmed even up to date. Now I will give you a set of maps and a property that is persistent, and this scheme is successful. So it does go on. So what the story is about? Our dynamical systems are Henon maps. H depending on the parameters, A is a complex number, Pn is a complex polynomial, of degree n, and this is a map of C squared to itself, and this is a one-to-one map, so-called automorphism. The formula is the following. So first of all, let us check that it is a bijection. That is, suppose that the image is ZW, then, and we want, so in order to say that it is one-to-one, first it is definitely one pre-image has one image. Now one image has only one pre-image. We take the image and we want to find pre-image xy. Then immediately y equals z, and minus ax equals to w minus p of y, but it is now z. And dividing by minus a, we restore x, so it is indeed one-to-one. Notice that this map differs a lot from the one-dimensional case. In dimension 1, when you map C to C, the only holomorphic bijections are affine maps. Z comes to alpha Z plus beta. But here you have zillions of one-to-one maps. The Hainaut maps are not the only maps that are automorphism of the complex plane. But by a rather old Milnor theorem, all the complex automorphisms of the complex plane may be expressed through the Hainaut maps. The story says that Hainaut maps appeared in the following way. When the Lorentz attractor was discovered in 60s, its chaotic behavior surprised everybody. But it required computers rather powerful in comparison with what everybody had. And a French mathematician or even physicist, Hainaut, said, why do you need so complicated formulas to demonstrate a chaotic behavior? Here is a formula that will give you a well-chaotic behavior too. And really, the behavior of the Hainaut mappings is chaotic, and many people study it. I will not say anything about this general study. I will discuss only a so-called Kupka-Smale property, or better to say, absence of heteroclinic orbits. So what I will discuss is the absence of heteroclinic orbits and first of all, I give first the picture, absence, I said in the wrong way, absence of heteroclinic tendencies. A fixed point may have two invariant lines passing through it. Better to say two invariant analytic curves passing through it. And the other orbits will go in this hyperbolic way. There may be another fixed point. And what may happen in general, that their separatrices do cross each other. And this is a so-called heteroclinic point. For brevity, HP. And this is a good picture, which happens in general for such maps. I plot a real model, but a complex analog also exists, as I will understand. And what is the bad picture? It is the following. Instead of intersecting this separatrix, another one is tangent to it. So this is heteroclinic tangency. This is bad. And our goal is to prove that there is no ball in the space of the Henon maps. This space is the space of all the maps of this kind with the fixed degree of the polynomial P. So we want to prove that there are no bad maps in a whole ball of the parameter space. Let me now define strictly in details this picture. I will now state the Adamar-Perron theorem related both with the real and complex plane. So it is a statement about what happens near a fixed point of a two-dimensional mapping. Consider a map, not necessarily the Henon map, say F. Now it is a local map of a neighborhood of 0 in C square to some other neighborhood. and f of z equals to the linear part of z plus higher order terms. And it is holomorphic. Suppose that A has two eigenvalues, lambda and mu. Magnitude of lambda is smaller than 1, and magnitude of mu is greater than 1. Then it is called a complex saddle. And the theorem has that F has two holomorphic separatrices. The real analog of the picture will be the following, and I ask you to imagine that this curve is in fact a disk embedded in the complex plane, and this one is also a disk. This is one interpretation. Another interpretation is literal. These are one-dimensional curves on the real plane. So if the higher order terms will be absent, then the linear map will be the following. You will have an eigenvector corresponding to lambda, and along it the points will tend to 0, and you will have an eigenvector corresponding to mu. Along it, the points will be exponentially go from 0. And the theorem is that in the nonlinear case, instead of the pieces of real lines, you have holomorphic curves. They are called W stable and W unstable. And the points are going along these curves to 0 and from 0. So the theorem claims that exist holomorphic WSWU such that f of WS belongs to WS and f of WU contains WU. So this piece is mapped to this one, and this piece is mapped to this one. The question whether the complex, we call this complex saddle. The question whether the complex saddle is holomorphically equivalent to its linear part is classical and rather difficult. Poincaré studied questions like this, but he could not overcome the case of the complex saddle. That was done only by Ludwig Siegel in 1942. But Poincaré overcame another case which is interesting for us. He overcame a case when both eigenvalues are greater in magnitude either greater than 1 or both smaller than 1. So the Poincaré theorem claims we have a map F again, Z to AZ plus higher order terms, and now say both lambda and mu, the eigenvalues of A, are greater than 1 in magnitude. Suppose that their ratio is irrational. Then the Poincaré theorem claims that exists a map H of a neighborhood of 0 to another neighborhood of 0, such that if you want to live in these coordinates, you bring the map in these coordinates to the map in these coordinates. For that, you go by H here. Probably, no, I want to bring F acts here, and I want that A will act here. So you take, F acts here, and I want that A will act here. So you take a point here, take its inverse image under H, then apply F, then apply H again, and you get A. The formula is the following. A is equal to H inverse, composed with F, composed with H. Once again, you take a point here, you take its inverse image under H, this is H to the negative 1, you apply F, then you look at the image under H, and the result is linear. Okay? There is the same theorem, same for dimension 1. You will just need A to be a complex number of the modulus greater than 1, and the similar theorem will take place, and we will use it. And now I want to show you just a step aside. So-called two domains. And I should say that this is one of the highlights of the lecture today. So what is Fatou domain? It is something in dimension 2 which is impossible in dimension 1. So what is impossible in dimension 1? It is impossible to find a biholomorphic map of a complex line C strictly into itself. If you take a one-to-one holomorphic map of C into C, then it is always onto and it is always affine, as I already said. So Fatou discovered that this is not the case for C squared. And you can take a biholomorphic map of C squared inside the C squared, and the image will be a proper subset of C squared. There will be a ball in C squared that does not belong to this image. So this is what is called Fatou domains. And right now, I will immediately show you, with the help of the Henon map, that the Fatou domain really exists. So, exists H, a biholomorphic map of C square into omega in C square, which is a proper subset. Now, I will show you the construction using the Poincaré theorem for the Henon map. So, here are two copies of C square. So this is proof. Take the Henon map with a fixed point zero as in the previous theorem, as here. And exists another fixed point. Fixed points of the Henon map are easily found if ZW equals to yx, then x equals to y, because x comes to y, and this is a fixed point. And if x equals to y, then the fixed points are roots of the corresponding polynomial of one variable. So it is easy to adjust a polynomial p to this construction, okay? It's easy to find a polynomial p with these properties. Moreover, it is easy to find it in such a way that h equals to az and so on, and values are greater than 1 in modulus and have an irrational ratio. All this may be done playing with the coefficients of the polynomial. Now we have here acts f, here acts a. We have here a neighborhood where f acts, and we here acts a acts on the whole C2. And we have the map H like this. It brings our neighborhood to another neighborhood of 0 here. Now, exists H like in the Poincaré theorem. Let us mark this by star. Now I will show you a trick which is called extension by dynamics. We take a point which is not in this neighborhood. As this map is conjugated to a linear one, the linear map with eigenvalues greater than 1 just extend the ball to ellipsoid, a larger one. And the conjugated map brings this domain, this ball, to some distorted ball. I wanted to determine H in this ball. Good. I take the inverse image of H, the inverse image of this point under F. Then I make the conjugacy, and I apply the linear map A to this point. And this will be the extension of H. And in this way, H may be extended by dynamics to the union of all the images of the first neighborhood C square 0 under all iterates of F. I have shown you the construction for one iterate, but it works for all iterates as well. N is any natural number. And this is a map omega. It definitely does not contain any other fixed points of the Henon map. So it is a proper subset. And this is a map on the union of iterates of this ball under the map A. But what is the union of iterates of images of a ball under the iterates of the linear operator with the expanding eigenvalues, with the eigenvalues greater in magnitude than 1? The whole plane. And we are done. We have a biholomorphism of a proper domain in C square, this is omega, to the complex plane C. Okay? So I want to make a small stop here. This is, in my opinion, one of the highlights of the lecture today. I have shown you sort of a miracle of complex analysis which has a dynamical origin. you have seen how to use dynamics to extend maps, and you have seen the existence of the Fatou domain, which is surprising, and I should say that it still seems to be surprising for me. So this is what I wanted to show you. Now, I have said that there exists a one-dimensional analog of the function mapping. We can uniformize the separatrices. Uniformizing the separatrices is the following thing. You have the map H, say a fixed point 0 of this map. You have its separatrices by the Adamar-Perron theorem. Once again, the eigenvalues are one is smaller than 1 in magnitude, another greater than 1. And you may take a coordinate here, and you have a one-dimensional map here. H restricted to W stable is zeta to lambda zeta, and so on. And we know by the theorem that I quoted that it is conjugated to a linear map. And quite in the very same way, extension by dynamics, we may extend the conjugacy of this restriction with the linear map to the whole complex line C1. And therefore, I do not say any details about that, that exists a holomorphic map H sub S from stable from C1 to the union of iterates and of the local separatrix at 0. So, about any separatrix, you can think as about globally embedded complex line. So now, instead of thinking that this is a symbol for the local separatrix of the fixed point, I think that it is a symbol for the global separatrix, which is embedded in completely strange and cumbersome way into C2. But in any case, it is a global embedding. And global coordinates occur on the separatrices. It comes this C1. In C1, you have, say, a coordinate tau, and you bring it on the separatrix here. So the points on the separatrix W are uniformized by the points from C1. And 0 point of C1 is brought to the singular, to the fixed point of the map. So occurs a coordinate tau on a separatrix of a complex saddle. If you have several separatrices, you will denote the corresponding coordinates by tau 1, tau 2, and so on. So this is uniformizing is the biholomorphic map of a domain of C1 or of C1 itself to the curve. So this, the uniformizing is done. I am a little bit cheating. Probably you noticed that. There is some small problem with the definition of the coordinate too. Do you notice that? When you have a complex line C1, you do not have a definite coordinate on it. You may have one coordinate, but you can another global coordinate on C1. What will be the relation between the two coordinates? You can express one through the other, and what is the expression? What is the relation between the two coordinates on C1? If Z is a coordinate on C1, then 2Z is again a coordinate on C1. You keep 0 point fixed. At 0, the coordinate is always 0. A linear map, yes. So this uniformization to 1 is well-defined modulo some linear map. We will move this garbage under the carpet and continue. Now I pass to persistence, to the subject from which I started the lecture, to what happened when we continue along a curve some geometric object. First of all, we do not say good and bad about anything. we take the Henon mapping of C square, and we take two fixed points which are complex saddles. And their stable and unstable separatrices may cross. When you iterate the Henon map, then this point will move along this separatrix to 0, but it will also move along this separatrix. So it will belong to this separatrix. And in fact, the relative position of two separatrices, both are invariant under the iterates, are the relative position is very complicated. Poincaré, who first discovered this phenomenon, wrote that he never thought such a complicated picture before. Our goal, there are many interesting questions related to the intersection of two separatrices. Our goal will be to continue the heteroclinic point. Let us denote it by, say, Q of H. It depends on the Henon map. We are interested in the following question. How this point behaves depends on the Henon map. This is the parameter space, the analog of the space in this first picture. And we take, say, let us call this parameter, multidimensional parameter by one letter alpha. We take H alpha 0, and we go to another H alpha 1, and the curve is parameterized by alpha. Better to say, alpha itself is parameterized by a real parameter, but I do not write this real parameter. So the question is taken a curve gamma in the space, let us call it H. Can we extend the heteroclinic point along this curve? So this is a persistence problem. It is unrealistic to say that we can to extend the heteroclinic point along any curve. But a theorem proved by Bazard, Hruska, and myself about 20 years ago says that the homoclinic point Q of H of alpha 0 may be extended along a curve gamma epsilon, epsilon close to gamma. So with the same origin, I do not write this. So this extension maybe is impossible, but such an extension is always possible. I did not want to speak on this subject outside this lecture. So I have about 10 minutes to end up the whole subject. It is impossible to end up it in the full detail, and I will show you only some pieces. First of all, this section will be called no tangencies. Instead of this picture in C2, which is a good picture, I plot a bad picture that I already have drawn. Now you understand what does it mean. Now I plot the space H, and I want to convince you that there is no ball with the Henon maps having a tangency like this. Suppose, on the contrary, that we have such ball. Now you understand what does it mean, the word bad. The ball consists of that Henon map that has heteroclinic tangencies for all maps from this ball. All of them, yes, all of them. Now, a part that I do not comment at all. There exists a ball which have no homoclinic tangencies at all. This is a part of the study of the Henon mappings, and I want to give you only very short commentaries. Look at the formula for the Henon mapping. And suppose that A is 0. Then the Henon map is no more a biholomorphism, because when we found the preimage of any image, we divided by A. We divided by A. So when A equals to 0, the image depends only on a one-dimensional coordinate y, so it is one-dimensional. So we come to one-dimensional polynomial dynamics, which is very rich. And using the tools of these dynamics first, and using the arguments that come that for small a, our map is two-dimensional but close to one-dimensional, we can prove that good domain exists. Now, let us bring the bad Henon map to a good one. We have this persistence theorem. So the this is still a homoclinic point, and it persists. And if there was a tangency for an open set of the parameters, then by the version of the uniqueness theorem for analytic functions, there will be a heteroclinic tangency along all the curves. So if the bad ball exists, then the heteroclinic tangency persists. And this is a contradiction, because you brought the heteroclinic tangency from bad domain to a good one where it does not exist. So we get a contradiction. And this is the way to prove that the heteroclinic tangency cannot be met in a ball of the Henon mappings. Let me give, this is the end of the main part of the lecture, and I want to give some comments. There is a famous property of dynamical systems. It is a Kupka-Smale property. Kupka-Smale is that all the fixed point and periodic orbits are hyperbolic, and there are no heteroclinic tangencies. So the study of the Henon map has two parts: algebraic part and transcendental part. The algebraic part is the study of location of singular points, of fixed points. Fixed points are roots of the algebraic equations, so they depend on the parameter in an algebraic way. You can extend them, the solutions, the roots of the polynomials are globally defined functions of the coefficients, algebraic functions. So the fixed point of the Henon mappings depend algebraically. Now you have an intermediate object, a separatrix. A separatrix is attached to the fixed point. But, so when you change the parameter, you can definitely follow the separatrix. The separatrix changes, but it changes analytically rather than algebraically. The separatrix is already a transcendental object. The heteroclinic point is completely transcendental object. It is an intersection of two transcendental curves. And the persistence theorem claims that this transcendental object behaves algebraically. So remember the persistence problem for complex limit cycles. Complex limit cycle is another transcendental object related to a polynomial vector field in the plane. We do not know whether we can extend it globally with respect to the parameter or not. And here we have another transcendental object, a heteroclinic point of the Henon map. It is a completely transcendental object, but we global persistence theorem, it may be extended globally with respect to the parameter. So I end with this commentary. Thank you.
¿Preguntas? Is there any question?
Hi. So can you say again why, one word on why does the heteroclinic tangency persist?
We know that this point, intersection point, it is an analytic function on the parameter of this curve. The tangent vectors to both separatrices are also analytic functions of the parameter. If the tangency takes place, then the determinant is 0. But the determinant is again an analytic function of the parameter. So by the uniqueness theorem, it is identically 0, so it is 0 along the whole curve of the parameters. Is it okay?
Any other question?
In both of the persistence problems, the limit cycle one and the heteroclinic point one, you mentioned the idea of supposing that there exists a ball where there is a bad property, and that we come to a contradiction. And if I recall correctly, in the real case for two-dimensional maps, the idea of structural stability is founded precisely on establishing equivalence classes and finding that given a point and an equivalence class, you can embed the point in a ball of its equivalence class. So is this like some kind of extension to the complex case of any idea of stability, of structural stability for complex case? Or am I just mixing things up?
I think that these realms of problems are different. I do not know any version of structural stability theorem, a theory for the Henon mappings, and I guess that there are domains where they are structurally stable and domains where they are structurally unstable. And here we ignore is our curve intersecting domains of structural stability or structural instability. So this is, so I think that some relation exists, but one problem cannot be reduced to another. We cannot reduce the extension problem to the problem of structural stability because our curve may intersect the regions of structural instability.
Thank you very much.
More questions? Well,
Sorry, Poincaré's theorem, you state that those eigenvalues must be on the quotient irrational.
This is for simplicity, yes, I quoted it, yes.
But I think that we can think that those eigenvalues are real, no? Even for more.
Yes?
Is there any version of this theorem that we could not require that those are rational?
Wait, well, I said this irrationality requirement only for brevity. Nobody states Poincaré theorem in this form. Nobody writes it in this form, including myself. So the correct statement is the following. The ratio of lambda and mu should not be integer or inverse to integer. And in this case, the conjugacy exists. This is the good formula statement of the Poincaré theorem.
Okay. Thank you very much.
Any other question?
Is it really that the ratio is irrational, or the logarithms have irrational ratio?
Well, forget about this irrational. I have said the statement that is written in a book, including mine.
Any other question? No? If no, well, let's thank Yulij again.
Thank you.